Welcome, everyone. This is the second part of our class on audio and health. So until now, we have seen how audio can be used to detect characteristics of our health, especially with respect to breathing, as well as wheezing, but mainly related to our voice. We've also talked about sleep briefly in terms of sleep apnea. In this part of the lecture, we will concentrate more on sleep, give another example and more extensive on how sleep can be detected through audio, but also we will look at the use of audio from other parts of our body, in particular aspects related to auscultation of our hearts. So I will also highlight that until now, we have mainly used the traditional machine learning approach that uses features and then traditional classifier. In the last part of the lecture, I will also expand on the use of more modern techniques of deep learning, which we've already seen in the lecture related to IMU. And here again, the issue for that is related to the fact that you might not have enough data again, but let's get to that a bit later. So in this work that is highlighted in a paper at the bottom, they are trying to do sleep stage classification with audio. And this is done with the use of, it's not really a wearable or a mobile technique yet, but it can lead to it. What they do is put a microphone on top of a bed, and they use that to detect audio of people sleeping in the bed, and then they classify it. The idea being that during the different phases of sleep, the resistance in our respiratory tract is different from when we're not sleeping. And so there is an amplification of air pressure oscillation during breathing, and you can detect those using sounds. As you probably know, there are various phases of sleep. There is a phase called rapid eye movement and a non-rapid eye movement phase, which is the deep sleep phase. And then there's, of course, the phase when you are in bed and you're trying to sleep and you're not sleeping. But in some cases, this could be because maybe you're lying still, this could be associated to or confused with sleep. So it's important to also distinguish that. So in REM sleep, the breathing patterns are more periodic and consistent compared to REM and wakefulness. And in the different types of body movements that could be detected even by audio in the case of wakefulness. So these are things that we hope to translate into audio features to then use to classify the different sounds. But first of all, the setup of the study is that the microphone is put on the bed, and here's a description of the details of the microphone. But also, how is sleep generally monitored in gold standard? I've hinted at this already when we talked about sleep apnea, and here is a picture that describes how the gold standard works. You have lots of straps and things to your head, EEG, and all sorts of aspects related to your physiological signals are detected. ECG, EEG, oxygen saturation, everything, and respiratory chest straps to monitor the sleep. So it's not a very comfortable thing to do. It's also very expensive to use. So finding a proxy to that that can be brought out of the lab could be a very useful thing to do. And here is, for that paper, here's the steps that have been taken. So you take the full audio sleep signal, you pre-process and reduce the noise in the usual way that we've seen. You try to detect the breathing as well as the body. And the paper describes, I guess, a bit superficially, a number of features that can be used to detect the macro sleep stages, which are these different phases of sleep that we have described. And the various features that are extracted are within breathing features, between breathing features, body movement features, background noising features, and other features. I'm not going to talk much about the real-time versus offline classification in this part of the lecture. So in the top there, there's a description of what one would expect to see in the different phases of wake, REM, non-REM. So the upper resistance, as we described in a few slides ago, is higher when we sleep than when we are awake. And so that is described in the first row there. The body movement is higher during wake time, but we do move when we are in deep REM sleep, non-REM sleep. Non-respiratory sounds, such as voicing, are existing mainly when you wake, but not while you are in those sleeping stages. And breathing pattern periodicity is actually quite different in wake time and non-wake time. And so we expect to see it in the data. So on the B panel, there's a description of the wake, REM, and NREM raw signal sound collected. And then obviously there's a pre-processing phase, and you can see all the noise reduced, and you can start seeing, especially in the REM, very clear pattern isolated there. The techniques used for the pre-processing are the traditional one. We're seeing them already a few times, but you can read about it in the paper if you're interested in the details. And then our well-known spectrogram defining the frequency-time relationship. You can see a very considerable difference in the frequency spread and description. And this is then mapped into the various stages of inhalation, exhalation, and body movement, and other activities detected by the noise. And this is very clear in the bottom part. How this is done depends on this feature extraction that we will talk about, but by just looking at this picture, you can immediately see how, if you have such a description, you'll be able to distinguish these three specific phases. And so in the next few slides, we will be describing the various features used. The paper does not go much into details of how these are mapped in more basic features of the signal itself, but these can be quite easily deduced by the self-explanatory description of what these features are. So the detection score of inspiration obviously will measure how much depending on those frequencies related to inspiration, you will use that to detect depth, and then detect the duration of the inspiration and the expiration. And we've seen a little bit of that already in the previous lecture as well. I notice here that there are the frequency spectrum and engineer envelopes are very much used to detect these already, and some are explicit, some are a little bit more explicit. The between breathing features that really describe the duty cycle are quite interesting. For example, the respiration period here is calculated using something that we've already seen, the autocorrelation, which finds the pitch period over time of the signal. And so although this is kind of a higher level feature, it's based on very basic signal processing features. And then other features are body movement features that are highlighted on the percentile, and here is a description of them. So here, all these features are then inputted into a fully connected deep neural network. And then there is a softmax layer that gives the probability for the three different phases. So how well does this work? Well, this is the example for one subject. At the top, you have the audio signal, enhanced, meaning that it's processed. And the first one is the probability of the signal being blue, wake, orange, REM sleep, red, non-REM sleep. Let's skip the look. We will only look at C, the fact that we have done it offline. So we take all the data and do the analysis offline. They also have a real time that obviously, as you can see, doesn't work as well as the offline, because in offline you have more data, you can make better description, better inference. So D is the ground truth. This is collected with the polysonography, so with all those wires. And blue here is when the user is awake. And so you can see the correspondence between C and D, which is quite well matched. Perhaps there are, one might say quite clearly that this blue line are not very well detected by this. I mean, there's a little bit here and here, and possibly here, but this one is perhaps could have been deeper here, essentially. But it works very well. It's just a microphone, is nothing else. So yeah, this is a very good result. So this kind of wraps up the work on sleep and sleep apnea. And we're now moving on to something related more with our cardiovascular health. So coronary heart disease is related to plaque building in our arteries, and this restricts our blood flow and therefore our oxygen, because blood carries oxygen to the heart. And so because of this might induce changes in respiration, generate irregular breathing, increase muscle tension in the vocal tract. And so because of this relationship, there is a possibility of hearing this in the participant's voice, especially when they are pronouncing sustained vowels. So sustained vowels means I'm saying ah, e, e. So when this is done, it might be possible to detect something in the data. And here I have a few features that are, in my review of the literature, recurring into the use of features into the detection and the use for detection of this sort of coronary diseases. So the fundamental, so I recap, fundamental frequency is the rate of the vibration of vocal folds. And we talked about vocal folds in the last lecture. And if we look at this picture on the x-axis, there is time, and this is the period of the vibration of the vocal fold, and 1/L is the fundamental frequency. So it's the inverse of the duration of this period. So you can average all the extracted fundamental frequencies period by period and have a measure, which is actually a good and nice feature. In relation to that, if you measure the distance, so how this value changes over time, you have a measure that is called jitter. And if you measure its amplitude change over time, you have a measure that is called shimmer. And distance measures are, studies have proven that by measuring these things, you are kind of describing roughness, breathiness, and hoarseness in a speaker's voice. So a couple of slides to talk about absolute jitter, which is the period-to-period variation of the period, essentially what I've just described. The fundamental frequency and how it changes over time describes the jitter. Shimmer is the same thing, but it does it for the y-axis, for the amplitude. And so in a study that is using this sort of data to understand the coronary heart disease distinction. So how is the voice of patients that have a coronary heart disease and healthy individuals? These are the results. On these two columns, you have the control group, so the healthy people, and here is the coronary heart disease group. And you see that the jitter and the shimmer are generally quite good at distinguishing. So this number here and this number here are very different, and this number here and very different. So there seemed to be a good intuition here that using this for coronary heart disease detection is a good thing. Same can be said for other studies that have used, for example, this sort of features for neurological diseases. So Parkinson's is a disease of the brain that leads to shaking, stiffness, and difficulty in walking, coordination, as well as balance. And hypokinetic dysarthria, HD, I'll call it HD from now on because it's a mouthful, occurs in quite a large number of Parkinson patients. And HD is correlated with less control of the larynx. And so it's related to the way in which we produce speech and our sounds. And so the flows that have been observed are related to increased acoustical noise, reduced intensity of voice, harsher and breathy voice, increased nasality, monopitch, monoloudness, speech rate disturbances. So the idea is that people have tried to translate these into features that can be automatically detected with audio. And I don't want you to read the details of this big table, but essentially, one thing I have highlighted here is that shimmer, which you know already what is doing very well. We talked here, if you look at the last column, this is accuracy, this is sensitivity, specificity of a task that distinguishes a Parkinson over the voice. And these are correlation coefficient and the significance of the correlation. And so shimmer correlates very well with a good significance, essentially. One thing I should highlight, and you will see more of it in the practical, is that there are now libraries that offer you features like we've seen. You can see the list here. You probably already recognize things we've talked about, this perceptual linear predictive coefficients. You might recognize the energy. You might recognize the jitter and shimmer, the zero mean crossing, the harmonics, the fundamental frequency. So we've seen quite a bit of that. There should be somewhere also the MFCCs. Here they are, the MFCCs. So there are libraries around that allow you to take sound and apply existing library of features to your audio, and then go and try to classify based on that. But essentially, these lectures are trying to give you an idea of what these features mean and what's behind it. A little bit, just a little bit. So until now, we have been talking about voice, but sound has the ability to say a lot more about our body beyond just voice. So we know that auscultation through a stethoscope has been with us for centuries, in fact. And that heart auscultation is something that doctors have been doing over the years. But it'd be interested to know that it's actually quite difficult to do. And this particular paper highlighted that trainee doctors from the US, UK, and Canada could only diagnose heart pathology only in 23% of the cases. So it's a difficult thing to do. You need skill, you need practice, but maybe a machine can do it better. So let's go back to the basics. How is the heart sound? What's the heart sound? So the heart is actually producing two sounds, which are called lub and dub. lub is created by the closure of two valves, which are the mitral and tricuspid valves, and the dub is the closure of the aortic and pulmonic valves. And so you might need to clarify that, for example, the use of electronic cardiograms, so all those wires, electrical wires that can be put near your heart and they can detect your heart signal, are not able to detect some of the pathologies that audio can detect. And these pathologies are related to the badly closing of some of the four valves that our heart has. And this is an example of pathologies that cannot be detected by normal ECG. You need either to do auscultation or you need an echocardiogram, so a scan, which is also quite expensive to use and difficult to, just not very portable. So can we do auscultation automatically using sound is what the next few slides are describing. So just so if you're familiar with ECG, this is just the correspondence of what's happening in PCG, so phonocardiogram, and echocardiogram. Photocardiogram is really the stethoscope stuff, and this is the ECG. So you have two sounds, one for the lub and the dub, and here are your sounds here, and again here. So there's a correspondence of this electrical signal followed by this audio, and again the same thing for the T. So for those that know their ECG very well, this is how it looks. So for the sounds of the first sound, S1 and S2, lub dub, then we have, this is the frequency distribution of the first sound, and this is the frequency distribution of the second sound. So even these two can be detected and distinguished. There is a difference in frequency that can be perhaps used to detect the two. So one of the things we've seen is the use of energy-based envelope calculation. This is just a version that has a log, and so it's Moosenet. But essentially, if you look at it again, S1, S2, S1, S2, S1, S2, there's a S1 missing here at the start. But what it does again is the flip all of it on the positive side, and then calculates the area essentially under this. And this is a very good measure that has been used in various papers, but we've seen something similar until now. And this is an example of paper from 2018 that has done that original signal, pre-processed signal. Sorry, it has detected a number of peaks using the envelope. And then it has, if you look into the paper, there's quite an ad hoc way to essentially get rid of these lower level peaks, which are clearly not the lub-dub peaks of our signal. And this is done mainly through a series of time-related features of the signal characteristics. You can read a little bit about it, but essentially it's like in this period, how many do we have, how distant they are, how distant they should be, how high is the peak, and by these characteristics they find the relevant peaks, and then obviously by sequence they go from first and second. So that's just for the peaks, but it's also important to classify, are we able to detect pathology, so this murmur of the various valves, using features and then classification. And here is a list of one paper's list of features that have been used. So some are time-based features, and some are just based on amplitude, the zero crossing. Actually, these are all time-based features, in fact. And so let's look at this table first. On the x-axis, we have the various pathologies, one might say. One is a murmur, one is an extra sound, extrasystole, and this is an artifact of the signal. And here the confusion matrix shows how confused it is, the detection. So for example, that we confuse fur murmur into normal, and one murmur into one normal into murmur, and you can see it's not too bad out of a 52. This is the error compared with other techniques that they use on 2 data sets, and they show that their error, which essentially calculate, well, they have in the paper description of how the error is calculated. It's expressed in seconds and equal to the value of the segmentation of the error in the sample. And essentially here what you can see is their approach seems to be better than others by using some time domain features. In terms of audio for heart, there are other features that have been used. And here is a list again. You might recognize a few, MFVCC, the spectrum, the autocorrelation, the zero crossing, the LFPC, shimmer, jitter. So these things are recurrent in any audio analysis you might want to do. So by selecting, one thing that has been done has been to try all these existing features on audio on the set of data and calculate them on the heart sounds. In this particular case, they came up with 6,000 features, but then they used principal component analysis, which we have seen a couple of lectures ago as well, to reduce the feature that are of importance to 500 features. And then they fed this to a fully connected network of about 6 layers and compared it to a traditional classifier. As you can see, in some cases, this is precision of normal, murmur, extrasystole, sensitivity, specificity. And you can see roughly, it's a mixed bag somehow of, and these are other works with respect to current work. We're really not looking at who is best here. We're trying to understand what can be done with this data in particular. Other things that have been done deep learning for audio are related again to generate vectors and matrices of features as input. And then they have constructed various DNA architectures to feed these features in, and then coming up to classify a task that is at hand. There's a good review on this, and I put the title in here if you're interested in having a look at various architectures used. And for the last bit of this lecture, I want to talk a little bit about something that we touched upon a couple of lectures ago. So on the fact that often, because we might not have enough data, especially not enough data in all the various categories, especially on we might have lots of healthy control data, but we might not have enough data of individuals with a disease or with certain classes of disease. Certainly it is true for heart as well as for many other respiratory breathing data. The data collection is quite small. So it would make sense to use pre-trained model or use self-supervised models or transfer learning also in the audio analysis. And you will see some examples of that in the previous paper that I mentioned in the previous slide. This is an example of a work we have done on respiratory sounds. So these were sounds we have collected from by asking people to cough, breathe, and read a sentence on a screen on their phone, and then record their sound. So we have some sounds of this kind. we feed them into a pre-trained model, which is called VGGish, is a Google pre-trained model. This model has been trained on a large data set of audio from YouTube. So it's really varied. It's nothing to do with just sounds of the voice, but it worked better than using other traditional architecture and use only our data. So it was better to use a generalist pre-trained model and then fine tune it with our data, and then feed our vectors into a dense, fully connected layer, and then use it for diagnostics. And also, well, I won't talk about the longitudinal study. Yeah. So if you're interested in knowing what this is about, we've actually used it to detect COVID-19 at the time. We did a large data collection, which is used by many other researchers. You can find more on my webpage or on covid19-sounds.org. And the idea here is, can we just use sound to detect respiratory pathologies? Any other test could be invasive, could be unsustainable because lots of plastic like antigens are quite unsustainable, or it might require someone to go somewhere for a test. Can we have something that is just based on your sounds? And the full picture of this, if you're interested, is that we think that the holy grail of all of this is a personalized model that can follow you, can have your voice when you're healthy, and then when you end up being sick, the tool will be able to detect the features of the change of the voice, and they'll be quite immediate and useful. Also, a longitudinal tool will be able to detect if you are improving. So if you're home with COVID and your voice is getting better, or your features in your speaking or your coughing or your breathing are getting better, then you would know that you're recovering, even before perhaps you feel the symptoms improving. There might be something in your respiratory tract that talks before you realize that. So that's the general idea of this sort of tools. I note that this doesn't only apply to COVID. Of course, it applies to many pathologies, especially some even chronic pathologies that can be monitored through this sort of audio tool. So in terms of audio, there is a lot of promise of this sort of tools for all sorts of body related sounds. We've also done a study on digestive sounds where we put a microphone on the belly and collect those. The interesting question there is often that the conversation with the doctors on what can we detect and diagnose using such deeper sounds that we probably never had at this granularity. So you have something that continuously produces, detects sounds from your body. This is something that the clinical profession is not used to have. So we sometimes don't know what to do about it. And we need to have this sort of conversation with the clinicians on how to create a discipline based around this. So this is, in fact, a very promising area. And I'll leave you with that thought. Thank you very much.